that because she's also made different contributions to this community apart from the scientific ones. She's also very committed to creating speaker opportunities for everyone in this field and so on. And she has been involved in several initiatives with respect to this, including, let me mention, the mentoring program that just was launched last fall and has been very successful and couldn't have happened without her work together with Mariana Graña and Michela Petrini from Paris as well. So, well, this being said, as I said, Irene is an expert on Swampland constraints and different applications for particle physics, and today she's going to tell us about the Swampland and the dark dimension. So, Irene, the floor is yours. Thank you.
Okay. Thank you so much, Álvaro, for the introduction. Thank you so much for the invitation. Thank you, everyone, for being here. So my plan, indeed, is to navigate you a bit towards the Swampland program, and especially those constraints that will bring me to this prediction of the dark dimension in our universe. So I'm gonna start very basic, assuming you don't know anything. The first part of the talk will be introductory, explaining what are the Swampland constraints that are necessary to motivate this dark dimension, and then later on I will get to the dark dimension. If you already know about the Swampland, just wait to the second part. If you don't know about it, then stay with me from the beginning and ask as many questions as possible. Okay? There are no stupid questions, so the more interactive, the better. Okay, let's use this since you already have it. Very good. So let me start with this question, which is what motivates in general my work and also this talk, which is, does quantum gravity matter at low energies? So the traditional answer that you give is, well, not much, right? Because we would expect generically that quantum gravitational effects become important at very high energies, Planck scale, 10 to 18 GeV. So the effects are going to be irrelevant. At low energies, it's very difficult to detect any quantum gravity effect, right? Now, the message of this colloquium, these general seminars, is that this is not really true, okay? This can be false, and quantum gravity can impose non-trivial constraints at low energies, even if the Planck scale is very high. And potentially, I mean, this is one of my long-term dreams, hopefully shed some light, for instance, into the naturalness issues that we observe in our universe. Okay, so I'm trying to convince you of this. You will tell me at the end of the talk if I manage or not. So, yes.
At the moment, we don't know the theory of quantum gravity. We have some hints for
yeah.
What you are going to tell us is going to be theory independent?
So the goal of the Swampland program is to be theory independent. Of course, that's very hard because there is no completely independent framework of what quantum gravity is. And that's why many of these constraints, we actually we say that they are conjectures because there is no way to completely prove them in full generality. But you can try to prove them in several setups. Like you can say, okay, imagine that it's string theory. Can I prove it in classes of string compactifications? Or imagine that I take some black hole arguments to motivate these conjectures. Or if I take holography, or then you can try to specialize. And the goal is to gather evidence from different approaches so that if from these different approaches you get the same answer, then you conjecture that that would be a general pattern and you try to understand if it's a model independent thing. So that's the goal. It's an ambitious goal and hard, but that's the goal. Okay? Very good. So, okay, so let's review a bit. Why we would expect that quantum gravity is irrelevant? Well, this is based on some expectation of separation of the scales, right? Which is based on a Wilsonian effective field theory approach. We love to do effective field theories, right? It's been very useful in the history of physics, just to formulate a theory that describes the physics up to some energy cutoff, without worrying too much about what happens at higher energies or smaller distances. Now, this Wilsonian approach comes together with this expectation, right, that the IR effective field theory, the theory at low energies, will not be very sensitive to what happens in the UV, so that you can describe atomic physics without worrying too much about what are the elementary particles and what is the mechanics of the quarks and so on. And so far this works very well in quantum field theory. Okay. And if you apply this to quantum gravity, I mean, if you think that this always works, like there is this sort of expectation of separation of the scales, then you would say, okay, if quantum gravity becomes important at the Planck scale, just put general scenario, then, I mean, this is too high in energy, so if I integrate out everything and I have a low energy description, it should not be important to understand this low energy description. However, the message is that even if this works super well in quantum field theory, gravity is different. Okay? And does not necessarily preserve this separation of scales. Why is this? Well, let me repeat the message. So the message is that quantum gravity can potentially break this notion of separation of scales, and that's why I say it can impose non-trivial constraints. So we have evidence from string theory. So string theory, at the very least, is a consistent theory of quantum gravity. Okay, you can use it as a theoretical framework, and there are many examples in which you see that there is like a UV-IR mixing. Okay, and that's precisely behind all the string dualities and like the regularization of quantum gravity itself. Like you can mix UV and IR divergences. But even before getting to the string theory, already heuristically, just thinking of black holes, you can see that this UV-IR separation is a bit artificial. Okay, so this is very hand-waving, but just to give some intuition. Okay, if you don't work in quantum gravity. So imagine that we collide some particles. We are used to the fact that if we put more energy, right, like we collide the particles at higher energy, we probe smaller and smaller distances. No? That's what we do in the colliders. But if you continue doing this, at some point, you are going to generate some black hole. And if you continue putting more energy into the system, this black hole is getting bigger and bigger and bigger. So instead of probing smaller distances, you start probing again larger and larger distances. Okay, so high energy then becomes correlated to large distance. And there is no, it plays this notion. So already, I mean, at the very heuristic, of course, you can try to quantify this much better, thinking of black hole evaporation and so on. But heuristically, you can see that in the presence of gravity, the UV and IR can be correlated. And if that happens, in particular, what is going to imply, and this is what I want to focus, is that not every effective field theory that you construct following the rules of quantum field theory is necessarily compatible with quantum gravity at a higher energy. So what do I mean with this? So imagine that you have like all possible effective field theories that you could construct for beyond the standard model of particle physics or cosmology or whatever. And you do it following the rules of quantum field theory, and you require they are anomaly free, whatever you want to require, get invariant, and so on. Still, the message is that not all of them, even if they seem fine at a given energy scale, not all of them necessarily can have a UV completion, okay, in a consistent theory, in particular in a consistent theory of quantum gravity. This is something which already happens in QFT, like in quantum field theory. Not everything is necessarily UV complete, okay? But the point is that if we are interested in UV completion in quantum gravity, these constraints can be even stronger than usual. It's not just about the tower of non-renormalizable operators. It can really have constraints on renormalizable couplings because this UV-IR mixing. Okay, so the theories that can arise as low energy limits of a consistent theory of quantum gravity, we say they belong to the landscape, while the ones that would not be consistent with a quantum gravity completion belong to the Swampland. Okay, and that's where the Swampland core is coming from. Any questions? Okay. So the Swampland is those apparently consistent, for instance, anomaly-free quantum effective field theories that Jets cannot be UV completed at higher energies in a consistent theory of quantum gravity, whatever quantum gravity is. Okay, that would be the formal definition of the Swampland. Now, the goal of the Swampland program is therefore to understand what is the difference between the landscape and the Swampland. So what are the constraints that an EFT must satisfy to be consistent with quantum gravity? And this is nice because, well, why I find this interesting is because apart from being an interesting question at the theoretical level, it can really have an impact in our universe, right? Because these constraints will be like a UV imprint of quantum gravity. And sometimes these constraints are surprising in the sense that they can go against what would be like EFT expectations, logic of naturalness, and all these type of things. So it's an opportunity to learn about our universe from quantum gravity. Now, there has been a lot of activity in recent years. Maybe you have heard this already many times, so I hope you will enjoy at least the second part of the talk. But been a lot of activity because it's like a new approach to connect string theory to the real world. Instead of trying to understand what is the concrete string theory vacuum that would describe the universe, you focus on understanding what are the universal patterns that any string theory vacuum should satisfy by consistency of quantum gravity, and therefore use that as a prediction for our universe. So if we are able to determine these constraints, then they could be used as guiding principles to construct new models and hopefully, shed new light into naturalness issues. So in this talk, I'm going to show you one example, okay, of this actually. So it's, using some of these constraints and so on, and I will explain all the caveats and assumptions that go into it. But if you take for granted some of these Swampland constraints, you can see how the logic of naturalness changes for the cosmological constant, and that's what will bring me to this prediction of the dark dimension. Questions? Yes?
Is this Swampland program done? Is it done arbitrarily in any number of dimensions for gravity, or 4D?
Yeah, so it's done in dimension, I would say bigger than 3, in the sense that you need to have dynamical gravity. Any dimension is fine, but for instance, 2 dimensions, all these Swampland constraints do not apply to 2 dimensions because, you don't have dynamical gravity, so it's like, again, it's more like a QFT in a sense. So you need to be able to have black holes.
And are some numbers easier than others, or is it the same game in all numbers?
It's not a matter of dimensions. What is easier, as usual, is, for instance, when you have supersymmetry or something like that, then you have more control. And for instance, for example, yes, if I will explain a bit, but you can take no global symmetry, like it's one of the Swampland constraints. So you can take some of the best understood Swampland constraints and then even try to classify the possible EFTs that you have, like even like a classification of possible effective field theories that you could construct. This is very hard to do in 4 dimensions, but in the case of dimension bigger than 7 with 16 supercharges, it's complete. Like you can have a complete classification of EFTs that would be consistent with the Swampland principles, and they match what you would get from string theory. So in those number of dimensions, because of the level of supersymmetry, it's easier has been done because there are less things to play with, there are less parameters, you have less freedom. So it's easy to do a classification. But in general, in principle, the Swampland constraints apply to any number of dimensions. It doesn't matter as long as you have dynamical gravity. Okay? Any other question? Okay, so what's the plan of the rest of the talk? So I'm gonna explain you some of these Swampland constraints. Okay? The goal at the end is to get to this prediction of the dark dimension, which is a large extra dimension in our universe of order n micrometer. And for that, I need to motivate what are the Swampland constraints that bring you to this, starting from the best understood one, which is the absence of global symmetries, and going through the distance conjecture, which is kind of a way to quantify how much symmetries must be broken, and this generalization, which is this pattern, that is what we'll bring to the dark dimension. Okay? So I will follow this route. And again, if you have any question, just interrupt. Okay, so how do we work in the Swampland program? Well, we want to understand what these constraints are. And as I was discussing at the beginning, I mean, of course, this is a very hard question, right? Because we don't have a completely universal framework of quantum gravity, so you cannot just derive the constraint from that. But we can try to gather data from all the approaches and, I mean, all the information that we have already obtained about quantum gravity in the past. So there are proposals for what these Swampland constraints would be. So what are the constraints that IPhT should satisfy to be consistent with quantum gravity? They go under the name of Swampland conjectures because, again, we can only prove them once we fit some setup, like some concrete quantum gravity theory. And then they are typically motivated by string theory, because it's a good framework for quantum gravity, and black hole physics. Okay? But the more approaches you can take to prove them, the better. Okay? So we try to understand how universal they are, or whether they are just features of string theory, or what's going on. Okay? That's part of the program, try to understand that. Now, the goal, I mean, typically what you do is you identify some pattern, maybe from thinking of black hole physics or string theory and so on, and then you use typically string theory as a laboratory to provide quantitative evidence for it. And then if you want to argue that it's something general, you also need to understand, at least heuristically, what would go wrong if you don't satisfy it. Right? So you try to use black hole, holography, something more general to understand. There is a question?
No. No problem.
I hope not with the Swampland program. And then you can also study the phenomenological implications, okay? Like at least you can say, okay, what would happen if this pattern would be true? What would it imply for our universe and so on? And that's, I mean, I will show you one example of this. Okay, so this is a map of most important Swampland conjectures. I'm just going to focus on the ones in purple in this talk. But I just put the map to remark that even if there has been like many different Swampland constraints that have been proposed and so on, I think the most important thing that we are discovering in the past few years is that they all seem to be connected. Okay, so even if they were formulated independently, some of them simply are related, which hints that they might just be different phases of the same quantum gravity principles that we are trying to discover. Okay? And it's more important sometimes the connections to try to extract what is behind than the conjecture itself.
You put links, but you didn't put any arrows. Who follows?
I didn't put any arrows because it depends on the case and was just too complicated. But you can ask me for it. Like,
I'm asking. So, is there anyone you can cross out?
Cross, like both barrels?
Like, say, look, this one completely follows
Yes.
from the other.
No global symmetries and completeness hypothesis. There were in principle two independent statements that were by Kuczynski and Cyber, no? You can see different statements. In recent years, we have shown, like for instance, in the case of having just a gauge theory, with any gauge group, we have shown that it's equivalent. Because using all these new type of global symmetries, like generalized symmetries, non-invertible symmetries, and so on, you can show that completeness of the spectrum follows if and only if there are no global symmetries. So this is one example in which this actually, I mean, yeah, this would be just one. And actually, correlation conjecture is also a way to formulate no global symmetries at the topological level. So all this first row is just one thing, no global symmetries. These two are related, but they talk about different data of your IPhT. So I really think there is just one way to formulate these two, but we don't have like a super good formulation yet. But I also think like, yeah, this row is gonna be the same, which is kind of quantifying how much you break the symmetries. Okay, and then these ones are just like different features that arise on the scalar potential, like on the landscape of Aqua, because of the presence of the states predicted by the previous two. So I believe that once you understand this very good, these two, you can just derive everything else as consequences of that. It's not like if and only if, but more like a consequence of the previous two.
So these relations are such that if I were to find, admittedly, a very contrived counterexample to one of them, it's not like the whole web collapses.
No, exactly. So here, that's what I said. Like here, these are consequences that appear in certain regimes. So the arrow would go that way. Like, I mean, this is more fundamental. And even if you find a counterexample of this, maybe it's because that consequence does not apply in that regime because it needs some special assumptions and so on. So these are like consequences in some cases. You need to understand very well when. These two, I think if you would find some counterexample of one of these, this would apply to the full row. So, and then if you have some, actually some counterexample here, like if you find a global symmetry in quantum gravity, I think this would also have an impact. Not the other way around, because this is like quantifying how much you break the symmetries. Right. So you would still have no exact global symmetry, but yes, the other way around. Yeah. And that's the goal. I mean, what I'm trying to do is also like try to understand what's behind, to reduce this to the minimal set of statements that will reproduce everything. Right? That's the goal. Like not to add more things, but to understand what's behind. Okay, now is the moment in which you can ask about the others, because from now on I'm only going to focus on the powerful ones. So if you want to ask something, you can, otherwise you can do it later at the end of the talk, or you be here to the end. Okay, so then let's focus on these two, which is the non-global symmetries and the distance connectors. Okay. First one. So non-global symmetry is the oldest, best understood, most motivated Swampland constraint. It says that there are no exact global symmetries in quantum gravity. So any global symmetry must be either broken, some high energy scale, or gauged. I just enumerate here the evidence for this. I mean, I don't want to spend a lot of time in the conjectures, but just to give you an idea, I mean, of course, there are no even potential counterexamples. Like string theory, we don't have any example of a global symmetry. At the perturbative level, you can prove it from the worksheet. That's already for Chisky book. More recently, you can prove this in IPhT in the context of splittable global symmetries, the CFT. So it's based on locality of the CFT. It's like a generalization of Nether theorem. And then recently, there have been, let's put even more works here, several works relating the absence of global symmetries to all these new works about understanding unitary black hole evaporation, reproducing the page curve with the wormholes and so on, because the wormholes, this topology changing transitions that you need to understand the unitary black hole evaporation are also breaking global symmetries. So, but I mean, these works try to show that if you have a theory with unitary black hole operation, then you don't have global symmetries and so on. Yes?
Does this apply to spontaneously broken?
No, spontaneously broken is like nothing. I mean, it's like exact, because this is for the theory, it's not for the vacuum. So if you have a symmetry which is just spontaneously broken, but apart from that, it's exact in the theory, that would be bad in quantum gravity. Okay? You need to explicitly break it, or gauge it, it will be associated with gauge.
So what's the status of dualities for the, like if I take string theory, come back to 4 dimension, I have E77.
So dualities, so a global symmetry does not change under dualities, because a global symmetry acts on the physical space, on the Hilbert space, so it's a statement which is invariant. And a gauge symmetry is not invariant under dualities, but a global symmetry is invariant, so it doesn't matter what duality frame you take, you should always find that global symmetry.
But I should think of this as its action on the spectrum of the, like, this global symmetry, right?
Ah, you mean if duality is a global symmetry?
Yeah, like
no, it's a gauge one, exactly, because it doesn't. So global symmetry. Okay, I'm gonna give you some intuition, but then the formal definition is that you need to have a topological operator, which with states, with operators that are charged under the symmetry, so that the symmetry acts on the Hilbert space, on the physical states of the theory.
So the RST is not in it either, because it
That's more
doesn't
like
act on the
gates.
physical.
Exactly. Exactly. That would be more like gates, like the global part of a gauge group, in a sense. Right? Or large systems for gates and so on. That's, when I say gates, I don't mean only the local redundancies, but also like the global part, large system formation and so on. That's kind of the gates. Okay? Because it doesn't act, doesn't have gauge invariant operators that are charged under it. Yeah, and recently I forgot to add it that there is also this paper of Juan Maldacena in which he takes one example to try to quantify how much symmetries are broken or so using the wormhole. Okay, so let me give you one intuition. I mean, as I said, like the formal definition, you can make this very formal studying topological operators, and there is a very clear distinction between what is global, what is gates, and so on. But just, this is the colloquium. There is I can give you some intuition so that in your head, very easy, you can try to understand if that's global or not. So how to distinguish if a symmetry is global or gated, right? The point is that you should ask yourself, like a thoughtful experiment, whether you can measure this charge from very far away. That's what it means that there is something that it acts on the physical states. Like you can have different types of symmetries, electric charge, angular momentum, some rotational symmetry, whatever. If you are able to kind of design in your mind some experiment that will be able to measure this conserved charge from far away, then it's a gated symmetry because you can carry the information far away. While if you cannot measure that, it's a global symmetry. Okay, that's like the intuition. So, for instance, electric charge, right, that you can measure from very far away because they have a Gauss law. And I know what is the electric charge that I have inside of this box, even if I don't open the box. So the point is that those that you cannot measure from very far away are global symmetries, and those are bounded quantum gravity. And that's why it also connects with kind of a holographic picture of the world, right? Because it's kind of being able to carry the information to the boundaries in a sense, right? Like, and that's why you can, I mean, I'm not going to enter into this, you can ask me, but there are many motivations based on black hole physics and so on, which rely on this fact, right? Because if you cannot measure it from far away, a black hole is blind to it. The black hole horizon is blind, and therefore you do violations with entropy bounds and so on. That's the point. Okay. Any question? So just to make it concrete, one example, this is the standard model of particle physics, right? I can think of this process. There are two conserved charges at the level of the standard model in this process. B minus L, baryon minus lepton number, and the electric charge, right? Both are conserved, but one is global and the other one is gauged. Okay, because I know I can detect what is the electric charge, right, from my experiment, but there is no way that I can measure B minus L unless I just count how many baryons and leptons you have. So the point is that these ones should not be exact. Okay, maybe it's fine at in the infrared, right, like in the IPhT, an approximate symmetry, but you should have either there are two possible solutions. Either it's actually gauged, so it can really be exact. Okay, so there is a new force associated to it, or it has to be broken at some high energy scale. Maybe proton is not stable, and so on and so forth. Good, very good. Okay, so no global symmetries, no exact global symmetry. You can say, okay, very well. This is, as I said, well understood. You can understand it in holography and so on.
I'm sorry. You said why there should be no global symmetries. I'm sorry, but I've not understood from your explanation. I mean, I know what is the global symmetry, I know what is the gauge symmetry, but I don't understand
So,
your motivation.
I put you here some evidence of concrete proof
Can
that
you give me the idea of the proof in perturbative string theory?
Yes.
Why there is a problem?
if you have the point is that if you have a global symmetry in the worksheet CFT, you can always construct a current by Nether's theorem, which actually implies that it's going to be gauged in the space-time. This is the procedure. So any global symmetry in the worksheet is always gauged in the space-time, in the target space. So there is no way to have a global symmetry in the space-time because all of them are gauged. That's in perturbative string theory. I can give you motivations like heuristic motivations with black holes. They are not proofs, but they give you more reason of what will go wrong if you have a global symmetry. For instance, if you have a black hole, as I said, a global symmetry is something that you cannot measure from far away. So what it implies is that the black hole horizon is actually blind to the symmetry, right? Like if I just have a black hole, even if it's charged under a global symmetry, the only thing that characterizes the black hole is the mass. Now, if that happens, you could imagine that you can construct many different black holes, many black holes with different values of the global charge. I can just throw different particles with different values of the global charge into the black holes. So I have many black holes, different values of the global charge. But if I let them evaporate and they all have the same mass, they all look the same because I cannot distinguish, I cannot measure this global charge from far away. And if I have a U1 global symmetry, that means I can have infinitely many black holes with any value of the global charge, any integer, and they look the same. So that translates into having an infinite entropy. Because like the entropy, right, it's like how many ways, broadly speaking, it's how many ways you have to create like the same black hole from looking from an observer from far away, how many microstates, and that will give you infinite. So it will go against Bekenstein entropy. You can also try to run arguments with remnants, stable remnants, the universe as well. Everything translates to having a violation of some entropy. And the problem comes from not being able to distinguish that global charge to be able to measure. And that's what gets us into contradiction when you use ADS-CFT, because you can have the global charge in the ADS, but I cannot translate this information to the boundary. I have an inconsistency on the duality. I have an inconsistency in the locality of the CFT. Okay?
Yeah, but I would say that the first one is string theory, the second one descends from string theory, the third one is semi-classical gravity.
Yeah. What else do you want me to add to the list?
Just to understand
Yeah, so far,
the proof.
as I said,
hypothesis.
it's that's why they are conjectures, right? Like I don't have a complete framework to prove you this. I can try to do it with string theory, I can try to do it with holography, I can give you semi-classical arguments using black holes, gravity, and so on.
No, I understand that the best you can do.
Yeah. That's what we have so far. Yes.
Let's talk relate all these examples of the cones. So if you have B minus L,
Yes.
suppose you gauge it, then we don't say engage was why gauge was not around, but what is supervisor dropping.
Or the coupling should be very, very weak, right? Yeah, and spontaneously broken, yeah.
Then let's say it's spontaneously broken, still it will carry no flux at infinity. Your black hole will still not see any charge. The carrier just doesn't go to infinity. It's massive.
You mean because it's massive, the gauge
Yeah.
field? Well, but then you typically have some discrete remnant.
Yes, sir?
The discrete part. So there has been work trying to understand, what happens if the gauge symmetry is spontaneously broken, so you have a massive gauge field. It's not really, as you said, not a long range force, right? So you say, okay, what do you mean with far away, right? Like I cannot really be super far away. But still you can have like kind of a Aharonov-Bohm experiments, which can detect these remnants like even if there is no, like, imagine that you just have a discrete symmetry. A discrete symmetry doesn't have a massless gauge field that is propagating, because you can understand discrete symmetry, for instance, from having a continuous one which is spontaneously broken and you just have a discrete remnant. But that still you can measure it. Basics and I have no problem. So that's something physical. Yeah. Very good. Good questions. Okay. So these are the arguments behind no global symmetries, but still they are arguments for no exact global symmetries, right? Now, if you want to apply this phenomenology, it's not very useful because I'm not telling you how much you have to break the symmetries, right? So one of the most important open questions here is, yeah, can you quantify how much the symmetries are broken, or if they are gates, how small the gates coupling is, how weakly coupled it is, what is the coupling? And that would give me an idea of what the scale in which I should detect the effects of breaking or gating. So this is main open questions. There are several ways to try to address this. This is an open question, okay? It's not completely universal answer for this. But one way to approach it is the distance conjecture. And this is what will bring us to the dark dimension. Okay, so the distance conjecture is very motivated in string theory, okay? So the way I want to introduce it is, yeah, like I want to understand what happens if in string theory you would try to engineer a global symmetry. So what goes wrong, okay? So imagine that you have your space of parameters, okay? You have different IPHTs, different values of the gauge coupling, whatever, different values. And imagine at some point, depending on what are the values of the parameters of your IPHT, you engineer some global symmetry, okay, of the theory. For instance, if I take a gauge coupling and I send the gauge coupling to 0, the symmetry that was gauged becomes global, right? So the question is, what goes wrong then? Okay, what happens, for instance, if I try to send a gauge coupling to 0? Okay, because if it's very, very small, I have like a nearly exact global symmetry, right? It becomes better and better, so it's like an approximation. Now, from the perspective of string theory, asking this question of what happens if I change the value of some parameters and so on, is like asking what happens when I move in the field space. Okay, so the point is that all parameters in string theory are parameterized by vacuum expectation values of scalar fields. So taking some gauge coupling very small, it's equivalent to say, okay, let's move on the field space, changing the value of the scalars in such a way that then this, for instance, this gauge coupling that depends on phi becomes small. Okay, so it's like moving on a scalar manifold whose metric you can derive it from the kinetic term of the scalars. Okay, like what you do with the Higgs boson, for instance, right? Like the massive you can parameterize in terms of the Higgs pair and so on. Okay, now these corners in which I will try to engineer like approximate global symmetries is what I'm gonna call asymptotic limits. Okay, and the point is that since I don't have, from string theory perspective, there are no exact global symmetries. Whenever I try to engineer one, like change the value of the scalar so that I would get an approximate symmetry, what happens in practice is that these regions are pushed to infinite distance in this field space. They are at the boundaries. So the global symmetries are only restored at the infinite distance boundaries of this field space. Push it as far as possible so that it doesn't really ever happen in a regular point. But still, this is interesting because you can try to understand what is the physics that arrives. Okay, maybe I cannot reach to infinite distance. I will not restore the global symmetry exactly. But I can try to understand what happens when I take the limit, right? And I go very far away. And what is the physics that arises? Whether there is some universal feature that forbids you to take the limit. And the answer is that in all these string theory examples, it seems that indeed what happens when you go to these boundaries in which you would restore a global symmetry, what happens is the cutoff, the quantum gravity cutoff of the theory, so the scale at which quantum gravity would become important, and you cannot have a QFT description anymore, goes to 0. Okay, so the better the symmetry is, the lower the cutoff of your theory can become. Okay, so that in the limit in which you could get an exact symmetry, the cutoff is 0. There is no EFT to talk about. Okay, that's I mean, just trying to extract the feature that arises. So even the message that even if these limits seem under control, like for instance, I have a glitch coupling which is very small, that's completely fine in QFT, right? Like I have a perturbative description, in principle, no problem with that. I'm telling you that you should be careful because small glitch coupling, even if it seems innocuous, is problematic in quantum gravity because you get too close to the situation of restoring a global symmetry, and therefore the cutoff of your theory should go down. Okay? So approximate global symmetries with decoupled theories come at a price. There is new light physics that forces this cutoff to go to 0. And this new physics acts as a censorship mechanism to restore this global symmetry. Yes?
This is very dependent on having string theory, or like a moduli space.
Right now, I'm exactly. Right now,
Do you have some intuition for why this generalizes to?
So, yeah, so now this came from string theory, and what I just said here is what is called the distance conjecture, okay? Now, you're gonna ask, can you give me some model independent argument of this, like why not the cutoff should go to 0 and so on? So, we've tried, in some cases, we have, now this is something very recent because it's really starting in string theory, we have given some black hole motivations for this, like for the presence of delta one, like the new physics, no, that forces the cutoff to go to 0. Like for instance, it's not completely universal because it's like, okay, let's focus on the case in which the symmetry is indeed a glitch coupling that becomes small. Then I could construct small black holes actually. When the glitch coupling becomes small, the area, classical area of the black hole goes to 0. And then you can try to run also arguments that showing that if the cutoff doesn't go to 0, you would violate Bekenstein bound. So you can try to derive exactly how the cutoff must go to 0 to be consistent with entropy bounds and other type of things. But it's very depending on what symmetry you are talking about. Like there is no universal argument. And that's one of the things that we really, that I find, well, trying to work on, like, that I would like to quantify much better. To have an intuition. Because if we have a model independent argument for this, for any type of symmetry and limit and so on, I think it's really going to make a big change on the Swampland program because this is what then gives rise to more important phenomenal implications and so on. So that's the. Okay, so what's the conjecture itself? Okay, this is what is called the distance conjecture. It says that whenever you go to infinite distance in the field space, which in the end is like trying to get close to restoring some global symmetry, you're gonna get an infinite tower of states that become exponentially large in terms of this proper field distance. Okay, so it's not just telling you that the cutoff goes to 0, it tells you how it goes to 0. Okay, so this is a quantitative statement because it tells you the cutoff decreases exponentially, okay, in terms of the distance that you travel.
Why an infinite tower?
Because if it's not, so if it was not infinite, if it was just a finite number of fields, you can always integrate in those fields and get a new QFT description. This is the scale at which there is no way to get a QFT with coupled to gravity. So what happens in practice is that this quantum gravity cutoff is associated to infinitely many degrees of freedom, so Einstein gravity completely breaks down. Like they cannot just integrate in these fields and have a new description. Finite number would not be enough. And then if you, from string theory perspective, I mean, this was formulated independently for global symmetries. Okay, now I'm connecting you and giving more modern perspective. But from string theory, it's just, it started as an observation. Like whenever I go to the limits, I find infinitely many states. So why is that? Okay. So, as I said, since I have infinitely many, this really signals like a drastic breakdown of the EFT. Okay, it's not just, I cannot just complete it with a new EFT. So it's why we call it quantum gravity cutoff, because I cannot have QFT anymore. And in practice, it kind of gives, I mean, you can also use this to provide upper bounds on the field range, maybe for inflation, other things and so on, which depend on what is the cutoff of the theory. Okay, so it's a correlation. Like if I want my EFT to be valid up to very high energies, then the distance that it can travel in the field space is smaller, and vice versa.
Sorry, all the fields in the tower scale goes to 0 with the same
Yes.
alpha.
Yes.
Okay.
At least that's what we've seen so far. I mean, that's the idea. That's the prediction. Now, since I was talking about this case of the gauge coupling becoming small, let me mention what it means here. If the symmetry we are talking about, if the infinite distance limit we are talking about is indeed about having a gauge coupling that becomes very small, so a gauge symmetry becomes global, then what happens is that I have a tower of state that is charged, so that as the gauge coupling goes to 0, the mass of the tower goes to 0, and in the end, what you can write is a relation between what is the value of the gauge coupling and the cutoff. So if you want to have a Billon standard model with some dark photon or whatever, depending on what is the value of the gauge coupling, you can tell that the EFT should break down at least at this scale, which is given by the gauge coupling. So it's a scale much below, that can be much below than the Planck scale. That's why I say that consistency with quantum gravity seems to impose constraints below the Planck scale at low energies, even if the Planck scale is very high. Because even if M Planck is very high, if the gauge coupling is very tiny, the quantum gravity cutoff becomes much smaller. The idea. And this is actually what is called the weak gravity conjecture, but I'm just motivating this from the distance. That's why I say in the end they are all correlated. And just to be clear, the symmetry that I'm talking about here is a zero-form global symmetry that was gauged, will become global. Or if you know about generalized symmetries, you also have a one-form global symmetry that is broken, becomes exact. Any questions? Okay, let's see. I have 10 minutes, 15 minutes?
15.
Good. Okay, so yeah, just give evidence. So as I said, this really comes from string theory. Okay, I would really love, and we're trying to work on other motivations beyond string theory. As I mentioned, we have some arguments of black hole physics. They are not completely universal. That's work in progress and so on. But it's just one example which from string theory perspective is very natural. These towers of states are there all the time. It's what is behind all the string dualities. They're very intrinsic from string theory. But we need to understand why this would be a general feature of quantum gravity. Okay, and so that's many people are working on it. Now, for the rest, 10 minutes and 15 minutes left, what I want to do now is to motivate the dark dimension. Okay, so this dark dimension comes from a refinement of this. When I have a vacuum energy, when I have it's not just like Minkowski, not flat space, but I have some potential energy, could be ADS or de Sitter, and it's about understanding what happened with this tower of states in that case. So, from string theory, it seems that if you have potential energy, when you move to these infinite distance limits, it's not only that the mass of the tower goes to 0, but the vacuum energy itself also goes to 0, and they are correlated. Okay, so at the moment, I mean, as I said, for the distance conjecture, we're trying to find black hole arguments that are independent of string theory. For this motivation here, let me be clear, I have no idea why it should be true beyond string theory. Okay, this is something very recent. You can take it as a pattern that's observed in string theory. In all these examples, you have this correlation between the vacuum energy and the mass of the tower of states. I would love that in the future I can give you some explanation why it's general. At the moment, maybe it's just a feature of string theory. I don't know. Okay? But this is the feature that will motivate the dark dimension. So, there has been, I mean, sometimes people call this also ADS distance conjecture or generalized, because there has been works like trying to show that independent of talking of the scalar fields and this space, maybe you can try to motivate this correlation by itself, like trying to show that having a very small cosmological constant, no, like a very small vacuum energy, is equivalent to go to some infinite distance limit in the space of metric configurations, and therefore you should get the tower of states. So this is what is done in this paper by Kumron and collaborators, and that's why they call it like ADS distance conjecture, because it starts in ADS. Anyway, regardless of all these motivations, the way I see it is that it's a pattern we observe in all these infinite distance limits. There is no clear bottom-up explanation for it yet. So from now on, let's just take it as a feature of string theory, and let's see what would be the implication if that would also be true in our universe. Okay?
Sorry, in the string theory examples, you also have computations of alpha, right?
Yes, I'm gonna show you.
It's not 10 to the minus
No,
5.
no, exactly. No, it's bounded. Yes. Yeah, let me, in a couple of slides, I will tell you what alpha is. So at the moment, just to be clear, so all known string theory examples so far, it occurs that if the vacuum energy becomes very small, it means that we are approaching one of these infinite distance limits, that we have an approximate symmetry, and there is a tower of states, an infinite tower of states, that becomes light polynomially with the vacuum, with the value of the vacuum energy. Okay? And this alpha, it depends on the type of limit that I take, and I will show you that there are some bounds for it. Okay, that's the pattern. Now, what I want to do in the remaining time is to explain, why this pattern is interesting, because it actually goes against the logic of naturalness, and what does it imply for our universe, which is this third dimension. Okay, so just quickly, when I say in all known string theory examples, what do I mean? I mean all known holographic ADS vacua. This V naught can be negative or positive. If it's negative, so I have like a family of ADS vacua. They always come together with this tower of states, because you have typically ADS times something, and the size of the extra dimensions is correlated to the ADS length. So these are like Kaluza-Klein towers that become light also when they take the flat space limit. So it's always happened so far. Maybe in the future we'll find a counterexample, but there is no counterexample yet. Even potential counterexamples of scale separation, they just mean that they have a different value of alpha here than we have scale separation. But this correlation with any value of alpha is always satisfied. You can take, of course, from string theory perspective, there are not many de Sitter vacua to play with, right? But you can think also what happens when you have like runaways, like time-dependent solutions with positive vacuum energy. In those cases, it also happens this. You have a positive runaway towards infinite distance. You'll also find these correlations. We have several works for n equals 1. Even without supersymmetry, okay, you would say maybe this is related to supersymmetry, because many of these string compactifications have supersymmetry and so on. There are non-supersymmetry string theories, no supersymmetry at all in space-time, that all of them also have this feature. You go to the flat space limit. I will give you one example. And even like there is this KQRT proposal for the Sitter, which is under debate, not clear if it's UV complete or not, but okay, it's a proposal for having the Sitter vacuum in string theory. Even that proposal satisfies this. Okay? So it's a pattern. And why I find it interesting is because it goes against string theory expectations, because I'm telling you here that the vacuum energy is of order when I have this infinite tower of states, right? They start with a mass m, imagine like a Kaluza-Klein tower, so I have m, 2m, 3m, whatever. I'm telling you that the vacuum energy goes polynomially, depends on the mass of the first state, right? So even if I have infinitely many, it's not that the heaviest states dominate, right? So these actually can be lower than the quantum gravity cutoff. Okay? So it's not that the vacuum energy becomes as high as possible in all these string theory examples. Now, why is this? Right? Like why you get this relation? I don't have like a universal answer because it depends on the case. Sometimes it's a classical contribution, sometimes it's quantum, but it's a interesting opportunity. I will mention this later, it's maybe with the neutrinos. So let me give you one example, because I don't want to take much time. I just want to give you one example, just one slide of a non-supersymmetric string theory example, so it's clear that it's not about supersymmetry, okay? In which you get this correlation, and then it's clear why the vacuum energy becomes small in a sense, right? It's not dominated by the heaviest degrees of freedom that you have in the theory. So why it goes against this EFT expectations, or against there's no fine tuning or anything like that. So just one slide. For instance, in string theory, you can take this non-supersymmetric string theory in 10 dimensions, completely non-supersymmetric. The heterotic string theory, you have just one scalar, which is the dilaton, parameterizes the coupling of strings, and you have a positive runaway. You have a vacuum energy, which is positive, okay, and decreases towards simple distance. Indeed, you have a tower of string modes. You have a tower of all the string oscillations, starting at the string scale. It also goes to 0 as you go to infinite distance, and you can compute the vacuum energy from like a Casimir energy from integrating out this tower of states. Okay, and the point is that when you do this, even if you have the infinite tower, right, you have to regularize the sum. Because modular invariance of the string, properly speaking, what you have to do in practice, if you were like an EFT person, is to cut the integral at the string scale. And like there is a quantum gravity cutoff, and even if I have infinite many states above, there is a modular invariance that relates heavy and light in that sense. And it means that the vacuum energy becomes proportional to the first state, to the 10, because they are in 10 dimensions, so this is the dimension of the space-time. Okay? So the lesson is that it's very important to integrate out properly the infinite tower of states. So the lesson is that the conclusion that you would get if you are an EFT person and just put some cutoff, imagine that we live here and I only know that I have the first two states. I don't know. And I integrate out only these two, I would get that the heaviest one dominates, right? If I have only a finite number of them below a certain cutoff, the contribution to the vacuum energy is dominated by the heaviest ones. But if I integrate out the infinite tower, the result is qualitatively different. Okay? And that's why in all these string theory examples, when you do it properly, you get that the vacuum energy is smaller than what you would get from EFT expectations. Okay? Any question? Okay. So, I think 2 minutes and I finish. So the scenario, you can say, okay, I don't know, let me take that maybe this is a general feature of quantum gravity, or at the very least, it's a general feature of the examples, I mean, what we know from string theory so far, and let's see what would be the implication for us. Okay? So one possible scenario then is that, okay, let's use this to understand why the cosmological constant is so small. So maybe it's small not because there is a fine-tuning of many contributions from different things in the landscape and so on, but just because it's a signal of being near some of these asymptotic limits, which is naturally small because I'm trying to restore a global symmetry, so the cutoff goes to 0, I have an infinite tower of state that goes to 0, and then the vacuum energy becomes proportional to the mass of these states. That is very small becomes very small, how small depending on how far I am in these limits, or how approximate the symmetry is. Let me remark that here I'm putting these triggers here because, of course, there are like some factors that depend on the model. Okay? This lambda will be completely model dependent. And maybe you can try to find a model in which you tune this lambda so that you lose the correlation between the vacuum energy and the tower of states. But the whole point here is that what is natural, like without trying to tune anything, is that the two scales are correlated. Okay? Then you can try to go around, but I'm trying to change what is natural from the perspective of EFT with respect to the perspective of quantum gravity. Okay, so could it be the case of our universe? Well, backing is small, that's nice. But then, if I want to use this to explain the smallness of the cosmological constant, it means that we should have this light tower of states, right? If the backing is small because we are trying to restore some approximate global symmetry, we should also have the tower of states. So is this compatible with our universe? Having such a light tower, because the cosmological constant in our universe is very small, right? So now let me put the bounds that were asked before. Theoretically, we can bound this alpha. And upper bound comes from the Higuchi bound because the tower of states includes like higher spin fields in all known examples. So unitarity in the sitter implies that the mass of the tower is bigger than Howard. So that puts a bound on alpha has to be bigger than 2. And smaller than D comes from the fact that if I don't tune anything, okay, like here I'm trying to avoid tuning or anything like that. If I don't have supersymmetry, I expect to have one loop contributions. And as I showed you before, when you integrate out the full tower, the result is that goes as the mass to the dimension of the spacetime. So at the very least, I will have this contribution, and that's why alpha is bounded with the dimension of the spacetime from integrating out the full tower. Okay. So what does this mean? It means that in our universe we should have, if that's a, I mean this is a scenario, so if we are in one of these limits, it means that we should have a tower of states with a mass between p to the 1/2, p to the 1/4, where this is the value of the cosmological constant, so it's of order milli-electron volts. Okay. So it is compatible with experimental constraints. There are two options. I could be talking of higher spin fields. No, the tower could be made of higher spin fields, but then that wouldn't be compatible because this is very light, so it's already rolled out by the LHC. But it could be made by particles, right? Like just like a Kaluza-Klein tower, like some decompactification of extra dimensions. And in that case, it's not ruled out because so these are the experimental constraints which are more constraining right now. They typically come from astrophysics, cooling of neutron stars, and so on, or deviations from Newton's law because they have an infinite tower of states, so it has an effect on gravitational interactions. And the bounds, even if they have a very different origin, it's funny that more than 2 dimensions is actually ruled out, but the ones that survive, they are of the same order. They are of order micrometers. So right now, experimentally, the window that remains, both from astrophysics and division of Newton's law, tells you that the extra dimension should be smaller than 30, 40.
The coupling are only gravitational. The coupling are only gravitational.
So here I'm assuming like the more general thing, which is that at the very least it's going to couple gravitational, and that's where the bounds come from. Now, if you start adding, like you can start trying to do models and other type of coupling and so on, and then it's much more constrained.
I guess I'm asking that if you know from the example in string theory whether these tower states carry other charges in the standard model.
The thing is that in the examples, I mean, I have in mind general examples in which I don't even know what the standard model would be in those examples.
Not a gauge group.
So typically from these examples, they are like, for instance, in this case, this tower of particles, they always signal some decompactification in some dual frame, right? So they are like a Kaluza-Klein tower. So it depends if the standard model gauge fields propagate on this extra dimension or not. That would determine how the couplings are. Typically, I mean, the scenario you have is that they do not propagate these extra dimensions in such a way that in the end the coupling is just gravitational. There is no gauge coupling or anything like that. So the most natural thing is that it's just a gravitational thing because it's just like a Kaluza-Klein tower of another extra dimension. Okay. So it couples to the Einstein term. Okay, so what's the conclusion? Well, the conclusion, let me do it pictorially so it's easier. Theoretically, we have this bound, okay, for the tower, mass of the tower. Experimentally, everything here, below here is ruled out, so the mass has to be larger than this, which means that the only region which would still be consistent with experiments is that you have a tower of states of a single extra dimension with a mass of order b to the 1/4. Okay? It's the only corner that remains experimentally feasible, which is good because it means that it's more constraining and you can try to rule it out in the future. So this is the last slide. If we live in a near an infinite distance limit, and then we use this to explain smallness of the cosmological constant, because all the story is all about approximate global symmetries, cutoff going to 0, blah, 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 blah. If that's the resolution, then you could explain that the cosmological constant remains natural in the mode. It's not like fine-tuning of contribution or anything like that. It changes the logic of naturalness. But then, you have a light tower of states. And the only value of the tower of states, which is both consistent with the theoretical experiments and experiments in our universe, is that the tower is of order b to the 1/4, which is of order b electron volts. Funny enough, this is the neutrino scale, which actually is a numerical coincidence in our universe, and the neutrinos seem to be, like the upper bound for the neutrino masses seem to be of order cosmological constant. So I don't have a motivation to tell you that this tower has to be correlated to the neutrinos, but it's just a tempting model that you can try to construct. Like, let's take a tower of right-handed neutrinos, for instance. That's still consistent with the experiments. So they are not charged under the gates, the electromagnetism or anything like that. It's just right-handed neutrinos, stellar neutrinos. But still, they can have some mixing, right, with the active neutrinos and so on. So that's one possible model you could construct to explain the coincidence. But regardless of that, that's more like model-dependent things that you can try to do. For sure, if that's the resolution of this cosmological constant, then it necessarily implies that since you have this tower of states, having like this infinite tower is equivalent to have like some large extra dimension for the inverse of the mass, which would be micrometers, and that's what we call the dark dimension. Okay. So let me conclude with this. So consistency with quantum gravity can have important implications that we are trying to discover. We hope to discover more in the future. We need to understand much better all these constraints to be sure that they are universal. This is a hard question, but at least you can take them as proof of principles of how, once you add quantum gravity into the game, you can have non-trivial constraints in low energies. Now you have to understand if that's a universal constraint or not. But for sure, like, if you take these classes of string theory, you see that there are correlations that are not trivial. And that's because there is this breaks this notion of separation of the scales. And I motivated this pattern, okay? You can motivate from the distance conjecture, quantifying how mass symmetries are broken, and so on. And right now, we just have evidence from string theory. It would be nice to understand if it's more general or not, precisely because it could have very important implications for our universe. So that's why I want to understand if it's more general or not. And if it's satisfying our universe, it would imply that we would have this extra dimension for the micrometers, which is marginally consistent with the experiments. And actually, since we published the paper, there has been a few experiments, like this one experiment that tries to improve all these deviations from Newton's law and get to order, I think, 5 micrometers. So, I don't know. Funny to see what will happen. So, thank you for your attention.
Questions? We already had a few, but last question.
So since you're building the company goes to 0, it's like gauge coupling goes to 0, then maybe the next dimension. And usually the other way around, like gauge coupling goes become large, you grow an extra dimension. Like duality. But so it's funny. And
what example you have in mind? Is coupling going large, going?
Between like gauge theory, strong couple gauge theory, an extra dimension.
I see what you mean.
This
Okay.
seems like the other way around. You lower the gauge coupling, you grow an extra dimension. Which I think it's curious.
Yeah, what you have in mind is more like holography, right? In a sense.
Yeah, it's saying that this is.
This is more. It's different. Yeah, this happens. Yeah, whenever you go. Think of the. I mean, like this gauge coupling can be even the gravity photon, for instance, of the extra dimensions. The gauge coupling of a gravity photon, right? The gauge photon goes to 0 when you take the radius to be large. But sometimes it's other things. You can have a P-form gauge field that the gauge coupling goes to 0. There have a weak coupling limit of string theory.
So my question is about what is the difference between this compact extra dimension respect to the others that you started with? Couldn't you just recommend everything from the beginning, from the start? Just one extra dimension? How would the theory would look like?
How is different in the sense
Maybe.
it's compact. I mean, the thing is that you're in a situation in which you have a compact dimension whose volume, right, is either going to 0 or becoming very large. It depends on the frame. Like the point is that there is always some dual frame in which you can think that this dimension is, the volume is becoming very large, so you decompactify it. And the question is, like how large it is. So it's still compact, right? But it's large. If you really take the limit, then it becomes non-compact and it is the same as the other ones, right?
Is it any different than let's say, the 6 dimension you compactify from 10 dimension to 6?
No, it's the same. It's like saying, imagine that instead in 10 dimensions, you compactify to 4, so you have 6 compact ones. But now I can be on different points in the field space in the sense that I can have different values for the volumes and the size of this extra dimension, right? And here I'm going to the corners, like to the infinite distance boundaries, which are the corners in which these volumes, or the sizes and so on, become extreme. In the sense that they become very large, or maybe ones become very small, but in a dual frame is like becoming very large. So it's like I'm focusing, and from all the EFTs that you could construct, I'm focusing on those corners in which the dimensions, like the dimensions become large, because there is some universal features that arise. Depending, it's like, I mean, any other point, okay, it's like I have a different model and it's very model dependent, but whenever I go to these corners, it seems that there are some universal patterns that arise, regardless of what limit, what dimension I'm talking about. And that's these universal features what we are trying to extract, because they seem to be model independent. Yeah, does this answer more or less?
So if one of the 6 quantified 6 dimension has this size, what would be the others?
Yeah, exactly. So here what I'm saying is that if we are, exactly, like I compactify, we start with string theory in 10 dimensions, we compactify to 4 dimensions. And the whole, in string phenomenology, you always try to find, okay, what is the 6-dimensional manifold, right, that would give rise to our universe? What is the size, the volumes, everything, no? Because depending on what I have there, I will have a different EFT. Now, what I'm telling you is that, okay, I don't know which one it is, but I imagine that I select those subset of EFTs that come from taking some limit in the sense that at least some of these dimensions are very large. Maybe 1, maybe 2, maybe 3, maybe 4, maybe 5, or maybe the 6 of them. There are different limits that you could take, depending on how many dimensions, how many of these volumes are large. I'm saying, if I now compare this with experiments, because in all these regions, all these limits, I will always have the tower of states, I can tell you that experimentally, all of them are ruled out, except for the case in which one of them is large, while the others remain, well, not super small, they remain order 1, I mean, like not in a limit. So the others will, exactly, so one of them is very large, so I'm in a limit for one of them, while the others remain small in the sense that it's not, I'm not in the corner of decompactifying or anything like that. I don't know what the value is, but it's not large enough so that I'm sensitive to the Kalusakain tower that would become light. The Kalusakain tower maybe it's a few orders below M Planck or further M Planck, so the others remain small. But one of them, so the only corner that remains consistent with experiment right now is that only one of them is very large. How large? 4 than the micrometer. And the others remain small. No, exactly. Not necessarily everywhere. It's just in that corner you get like a vibration. So even if you don't have a direct product, like the calamilla is 1 times something, right? Uh, you can still in a limit, right? When you take some modules to become large, you can get a vibration arising that limit so that there is one extra dimension becoming large. Like for instance, the FTOD limit itself is one example of this, right? I can take I have some compactification and theory, the Caravillao. I take the theory limit, which means that I'm going to grow 1 extra dimension. And that would be one example of such a limit, but there are other cases in which it's a matter of classifying. Like we have all this classification of infinite distance limits, and you can study the vibration structure in the limits and see which ones correspond to growing 1 extra dimension or 2 or 3 or just perturbative string in not growing dimensions. So there is a classification in terms of the local vibration structure that arrives. Sorry, say again. Yeah. I mean, yeah, the Laplacian equation of the to see the. Yeah. No, it's not necessary that every compactification has such a limit. Indeed. Like, not every Calavillao necessarily has an infinite distance limit in which you grow 1 extra dimension. It depends on the intersection numbers and so on. So it's just like you can classify all possible infinite distance limits that you could have, and this is the one that's still consistent with the experiment. Doesn't mean that every compactification has such a limit. So you can also use it to rule out what type of compactification if you want. Would still be consistent. That's a hard question, but in principle, a priori, you can use it for that as well. Yeah. So indeed, not always happens. Yeah. It's only part of the landscape. And tomorrow in the technical talk, what I will do is actually to explain all this distance conjecture. There has been a lot of progress on understanding what are the possibilities, sharpening, like not having ambiguities anymore with order 1 factors and so on, and looking at it from a global perspective, like for the full modular space. So you can also use it to rederive the dualities, what limits you have, and how to get information about AD escape separation and other things. And it's about classifying what are the possibilities and understanding if I have this limit here, what else could I have? Things like that.
Okay, quick question, please. Can you repeat what is the motivation for identifying the tower of flat states with the neutrinos?
Well, it's just a coincidence on the value of the mass. So I'm saying that from this perspective, there should be a tower of states whose mass like the first state of the tower, is of order the cosmological constant to the 1/4 in Planck units. And if you put the numbers, that's precisely the mean electron volt, is the upper bound for the neutrinos.
It's the mass of the active neutrinos, which is around 50.
Exactly, so it's like...
This does not tell you anything about the mass.
No, so the idea is that then maybe what happens, it's just some model, because the scale is mass, it's just a matter of matching. It could happen, one possible model you could construct is that you have some tower of states, and the first ones are active neutrinos, while the rest are sterile neutrinos. So what you call active or sterile, right, it depends on whether it's the first one or the rest. So then our neutrinos would be the first state of this infinite tower of states.
Don't it be strange because it would mean that not all, the states in the tower would not have the same left quantum numbers. So the right ones would be SU2 doublets, and the easy ones would be.
No, exactly. It's for the right-handed. So I'm thinking of I'm thinking of having so again it's the same. Like you can have the left-handed, like SU2 doublets. I don't mean that you have like an infinite tower of SU2 doublets. I mean that would be ruled out actually, because then you have the electrons as well. It's just that you can engineer to have like a generalized, like an extended mass for the neutrinos, including both the Dirac mass and possible Majorana masses, okay? In which you mix the handed part with the right-handed, including all the Majoranas, that is like an infinite matrix. And the solution is that, in practice, it's like if you have for instance, you have the standard model with the left-handed and so on living on some brane string theory, you have an extra dimensions, it's like all the rest of the tower, like the Caruso-Klein towers, are propagating this extra dimension. So all the sterile neutrinos will be propagating the extra dimension, and everything that is on the SU2 doublets would be localized on the brane, because are like the zero modes. Higher modes are propagating the extra dimension. You can engineer, people before this, like people try to engineer models of that, like see, okay, can I extend the neutrino sector by adding this infinite number of sterile neutrinos? There's some papers of Dine and other people doing this and studying the solutions. I can show you the reference.
But the relation of the mass in this tower is M to M, 3M, or something else?
So
so you have a 1 million M.
It's a Caruso-Klein tower. Okay, yeah. You could say it's a Caruso-Klein tower of 1 dimension, which simplifies a lot the question, because if the resolution was that it's a Caruso-Klein tower of 5 dimensions, then it's very complicated because there are many types of 5-dimensional manifolds, and the spectrum of Caruso-Klein can be much more complicated. For 1 dimension, you have the circle or the interval, and if you compute the Laplacian equation and so on, you get this like some exactly. Just because it's 1 dimension, it's possible to answer the question.
Okay, so then let's thank Irene again.